Good morning, good afternoon, and good evening. My name is Matkan Tercioğlu. I will be the session chair for this session. It will be, this is just to make sure that everybody is on, click on the same link. This is for research session 4, Graph and Social Networks 1 session, and we will have 5 papers in this session. To prevent Zoom issues and so on, the way the session works is that each of the authors submitted 15-minute videos that we will be playing. After that, we will ask questions to the authors. I will introduce each paper based on the list on the program. And then once the video played by the host, Bo, we would open up for questions. So please type your questions during the presentation to the chat window, and I'll ask them to the authors. I'm not sure whether the first author is here, but in the interest of time, I will start introducing it. So the first paper is exploring final granularity with coarse efficient KB core computation. Hello, are you online? Hello, is there any question? Okay, I think there was some thing. So the first paper that we'll be doing is from Zhang, exploring final granularity with coarse efficient KP core computation. Just a brief introduction. Chen just graduated from University of New South Wales, and her research area is graph processing and mainly focus on community finding. So, Bo, please share your screen and start playing the video.
Good morning, everyone. My name is Chen Zhang from the University of New South Wales. Today, I'm going to present my paper exploring finer granularity within the coarse efficient KP core computation. This is a joint work with Fan Zhang, Wenjie Zhang, Boge Liu, Lu Qin, Ying Zhang, and Xueming Lin. Here is the outline of today's presentation. First, I will show the motivation of this paper. Second, I will give the problem definition used in this paper. Then I will introduce our algorithms to solve the problem we proposed. Finally, I will show the experiments part. Graphs are widely used in our life. For example, in social networks, in e-business, and in biology. Cohesive subgraph mining is a fundamental graph problem aiming to extract highly connected structures from large graphs. The cohesive subgraph model of K-core attracts great attention due to its elegant property and linear time computation. In this example, we can see a 3-core. Nevertheless, in a real-life social network, the same degree constraint K may affect different to users with different skills of degree in a network. An empirical study validates that a large degree user usually needs more friends than a small degree user to motivate him to adopt a certain behavior. Thus, in the K-core model, the single degree constraint K may not be sufficient to ensure that every user in the K-core is well engaged. Motivated by the above facts, we propose and study a novel cohesive subgraph model named KP-core. First, we give the detailed definition of the K-core. That is, given a graph J and an integer K, a subgraph S is a K-core of J if we have a subgraph that every node in S has a degree larger than or equal to K, and S is maximum. Here we give an example of a 3-core. The definition of fraction is that given a graph J and a subgraph S of J, the fraction of vertex V in S is defined as the degree of V in S. divided by the degree of V in J. The definition of KP call is that given a graph J, an integer K, and a decimal P, a subgraph S is the KP call of J if every vertex V in S, it satisfies three constraints. First is a degree constraint, which means every vertex in S has a degree larger than K. Second is a fraction constraint, which means the fraction value given is larger than P. And third, the subgraph is maximal. In this paper, we mainly focus on three aspects related to the KP call problem. We compute the KP call of J with specific K and P values. We do the KP call decomposition that retrieves the KP calls of J for all possible pairs of KP values where K is between 1 and the degeneracy number of the graph and P is between 1 and 0. We construct the index for a fast KP call query and the maintenance of the index on dynamic graphs. Next, we came to the algorithm part. First is the KP call computation with given K and P. Here is the pseudocode for computing KP call of J. We first compute the combined degree threshold for each vertex, which is the larger one in K and P times the degree of V in J. For each vertex with insufficient degree values, we delete the vertex and its incident edges. The deletion of a vertex will decrease the degrees of its neighbors by 1. Once the degree of a vertex V does not satisfy the degree threshold, we continue to delete them until all the vertices satisfy the degree threshold. According to the definition of KP call, the containment property is immediate. Given a graph, if K prime that is larger than the given K and P prime that is larger or equal to P, the K prime P prime call is a subgraph of the KP call. Although the input K ranges from integer 1 to the degeneracy order of J, and the input P ranges from 0 to 1 continuously. Many KP calls are exactly the same with different inputs of K and P. Here is the algorithm for KP call decomposition. The decomposition is compute for K from 1 to the degeneracy number of J. Since the KP call is always a subgraph of K call, the largest value of K is dj, and the decomposition with fixed K can be computed on the K call of J. Every time we find the minimum fraction value among all the K call vertices. For each vertex with degree less than K or fraction not larger than the P minimum in S, we record the P number of the vertex by P minimum and remove the vertex from S. After deleting all such vertices, we find the next smaller fraction value again and follow the process to delete vertices. We repeat this process until S is empty. Finally, we return the P numbers for every K. Here we show the decomposition result of a 3 call. Based on the decomposition process, we can get the KP call index like here. It maintains all the P numbers and the corresponding vertices for every K. The index consists of degeneracy numbers of arrays, where each array contains the vertex set of K call and the unique P numbers of the vertices. In every array, the vertices are ordered by their deletion sequence. Then we come to the maintenance of KP call index. A real-world graph can be highly dynamic, where new vertices and edges are inserted to the graph, and some existing vertices and edges are deleted. We use UV to denote the edge that is inserted in the graph. For example, here the edge V5 and V11 is inserted in the graph. The following implies that some arrays in the KP call index remains the same with the insertion of uj. Given a graph J and an edge UV that is not in J, when UV is inserted, we get a new graph J plus. If the call number K is larger than the call number of UV in J plus, the insertion of UV to J does not change the P number of any vertex W in the array. Here is an example. After the insertion of V5 and V11, array 4 does not change as 4 is larger than the call number of V5 and V11 in the new graph. Insertion process mainly has two cases. The major case is call number keeps the same. In this case, the insertion of UV does not change the call number of any vertex. Then for each AK in the index, we find the P minus number range from P minus to P plus, such that a vertex in AK with P number less than P minus and larger than P plus will not change. Therefore, we aim to find a larger P minus and a small P plus. In subcase 1.1, we firstly present the techniques for K is less and equal to the minimum of the call number from U and V. Given a graph J, a degree threshold K, and an edge UV to be inserted in J, when P minus equals to the minimum value of the P value of U and V in array K in J, for any vertex with P number less than P minus, the insertion of UV will not change the P number of W in A. Then we prove the P plus. Given a graph J, a degree threshold K, the K call of J and a vertex W in the K call, the P hat upper bound of the P number of W is defined by the given equation. To explain the equation, here is an example. In this example, given an input K, we show vertex V1 has its 6 neighbors in the K call. The P number of each neighbor is shown in the figure. Suppose the degree of V1 is 6. We find that V1 has 3 neighbors with P numbers not smaller than 0.5. Thus, the P number of the upper bound of V1 is 0.5. Given a graph J, a degree threshold K, and edge UV to be inserted, let J plus equals to J with the inserted edge UV, and P plus equals the minimum number from P UK in J plus and P VK in J plus, P NUK and P NVK. For vertex W with P number larger than P plus will not change its P number if UV is inserted. In subcase 1.2, we deal with K is larger than the call number of U and is less or equal to the call number of V, and we suppose that the call number of U is less than the call number of V. In this case, the P minus number of V may decrease. Thus, we have P plus equals to P number VKJ. The value of P minus can be found by the following theorem. It's similar to the one before. Case 2 is the call number changes after the insertion of an edge UV. The P minus is set to 0 and P plus equal to PNVKJ if the call number of U in J is less than the call number of V in J, and P plus equals to the minimum from the P hat of U KJ plus and V P hat of VKJ. If call number of U in J equals to the call number V in J. Due to the time limit, we do not show the deletion part, and it's similar to the edge insertion. We conduct extensive performance studies to evaluate the effectiveness of our proposed algorithms. The table shows the statistics of the datasets ordered by the number of edges. We compare the KP call with K call since it's the base of our model and also the most related model. Specifically, we evaluate the following algorithms. This is the case study on DBLP database. The vertices of K-call are marked by dark gray and blue. The vertices of KP call are marked by the blue color. The light gray vertices are the one-hop neighbors of the K-call vertices, which help to illustrate the connection of the K-call vertices to the rest of the graph. The size of each vertex in the K-call reflects the fraction value of the vertex. We can say that the KP call has a larger density. We compare the computation time of K-call, KP call, KP query. We can say that KP call computation is slightly slower than K-call computation because some K-call vertices are deleted in KP call computation. The efficiency of the two algorithms are quite close because we can use one combined vertex threshold to conduct the KP call computation, which is as efficient as using the degree threshold K in the K call computation. KP call query outperforms the other two algorithms in runtime by more than one order of magnitude because its time cost is linear to the size of the output. We show the effect of different K and P to the algorithms on a data set. The time cost of K-call computation and KP call computation both increase with the larger input of K as they need to remove more vertices and edges. The runtime of KP call computation becomes slightly higher with the larger input of P due to more deletion steps. The running time of KP call query is much faster and almost the same for different K and P values. We compare the decomposition time between KP call decomposition on all data sets. We can say that KP call decomposition costs more time than K call decomposition because it conducts degeneracy times the decomposition for P numbers. To test the scalability of K call decomposition and KP call decomposition, we vary the number of nodes by randomly sampling nodes from 20% to 100% on the data set. We can say both algorithms are scalable on the given large data sets. In this experiment, we randomly remove 500 distinct existing edges from the graph and then insert them back. To test the time cost of the index update, we report the average processing time for one edge insertion and removal, respectively. KP call decomposition is used as a baseline algorithm which computes the KP call index from scratch for each edge insertion or deletion. The results are shown here. Our proposed KP call maintenance algorithm can achieve up to 2 orders of magnitude speed up compared with the baseline algorithm. We sample the graph in the same way as in the scalability test of KP call decomposition. This figure shows the results on a data set and the trends are similar on other data sets. The result shows that our proposed index maintenance algorithm are as scalable as the decomposition algorithm, KP call decomposition. This is because our algorithm is always visit a small part of the index for update, which is proportional to the size of the input graph. We propose and advocate a novel cohesive subgraph model, KP call. We analyze the KP call subgraphs from hierarchy structures regarding to increasing p-values for a given k. We propose an index with OM space cost and index maintenance techniques to answer KP call query over large dynamic graphs. Comprehensive experiments are conducted over 8 real-world datasets to demonstrate the effectiveness of our KP call model and the efficiency of our algorithms. Case studies are also reported on real datasets. Thank you. Good morning, everyone. My name is Chen.
Sorry, I'm mute. I think this went a little bit over, I guess, this talk. I think Chen on the line. Are there any questions from the audience? If you have, please type, I can unmute, I guess. I've seen that Chen is on the line. I have a quick question, Chen. I'll unmute you as well. We can answer directly. So you can unmute. So my question is that it looks like you have a new definition called KP core, and it finds different nodes as important. So how do you have a measure of whether the nodes you found in the KP core model is better or more important than the ones that are found in K core? So how can I have an independent evaluation of the importance of those nodes?
Oh, yes. Actually, we have done some experiments to prove it has better graph density, a better clustering coefficient, and we have shown the experiments of the granularity, like in a data set called GOLA, but I didn't show it in the experiments. It's in the paper.
Okay, I think I'll take a look at that. And also after this, there's a Slack channel associated with this session. So I encourage authors and the people who are there to continue the discussion after this if you have any further questions. So please check the Slack channel after the meeting.
Okay.
Thanks, Chen.
Thank you.
If there's no more questions, I'll go back to the next talk, which is, let's see, on my notes. It's paper 29. It's Joanna Trindade will give the presentation. I'm so sorry for butchering the names. Just to, this will be Kaskade graph views for efficient graph analytics. Joanna is a PhD student in ECS at MIT and working with Professor Sam Madden and Prof. Julian Shan. And her research interests involve around performance aspects of data processing system, primarily focused on query optimization and performance techniques for graph data management. So I will stop here and Bo, please play 29.
Good morning, everyone. My name is Joanna, and I'm here to talk about Kaskade graph views for efficient graph analytics. This is work that was done in collaboration with Costas and Carlo at Microsoft Ray Systems Lab, and Sam and Julian at MIT CCL. The agenda for our talk has 3 parts. However, if you need to leave early, here's a summary. The motivation for our work is queries over large machine-generated graphs are increasingly more relevant for operational decisions, yet they remain expensive to answer. We noticed that these graphs are highly structured, and we can use that for query optimization, however. And by using the techniques we propose, we can get performance gains of up to 50x faster response times, as well as orders of magnitude size reduction. So if you're staying a bit longer, we'll dive into more details. These large data lineage graphs are extracted daily from a massive amount of production system logs. How massive? Well, in a single week at a production cluster at Microsoft a few years ago, there were over 3 billion vertices that included jobs, files, machines, and tasks, over 16 billion edges between those entities, as well as an on-disk footprint of over tens of terabytes. These lineage graphs are increasingly more valuable for many operational decisions, which include scheduling, provisioning, debugging for incident response, for example, debugging data corruption errors, as well as even more recently mandates such as those from GDPR. And what you're looking at here is a visual representation of a query on that data lineage graph. And in this case here, if job 1 fails, jobs on its downstream may be impacted, and we'd like to know which ones those are. This is a simplified version of that job last radius query. It's written in Cypher, the graph query language. If you're not familiar with it, we're going step by step here. So first, we define a graph pattern as a collection of vertices and edges. We're saying, hey, the source for this graph pattern is a vertex of type job, and it connects through an edge of writes to a vertex of type file. That same vertex is anywhere from 0 to A hops away from another file vertex, F2. Finally, F2 connects to a J2 job by this is read by edge. The paths in this graph are explicitly following a producer-consumer relationship. And what we're trying to get here is all the dependency jobs in this sort of data flow in the graph that are in a job 1's forward data lineage up to 10 hops away. Now, on these large graphs, even the relatively simple blast radius query is expensive. How expensive? The distributed relational engine that we use at Microsoft took hours to answer it. And there's a number of reasons for this. There's a few that we're listing there. But essentially, traditional relational engines, they produce fairly inefficient plans when you're talking about graph structured data and you're trying to answer long path queries over that data. And existing graph databases do a little bit better, but they're still limited in scalability. So fewer are distributed, and those that are, they usually tend to rely on Prego-like programming paradigms that exchange a lot of messages between vertices. This works great for label propagation, but not so much for these types of queries that the folks at Microsoft had in mind, as well as other large cloud service providers. So to be used for operational decisions, these queries require short response times, order of seconds to minutes, certainly not hours, and definitely not days. So to solve these challenges, we observe that these graphs are highly structured. Here are some examples of structural properties. They have a fixed schema with edges that restrict the types of vertices that can be connected. And tightly coupled with this, the degree distributions and cardinalities for these vertices are fairly predictable. And we can use that information to establish that dependency chains follow a specific type of pattern or a fixed sequence. And we can use that for query optimization. So specifically, we can rewrite queries in terms of sparser graph views that we estimate to be beneficial for multiple queries in the workload and that are correct by construction. So going back to the running example for this presentation, if it's run over the original data lineage graph, and this picture you're seeing here is a 20,000 edges sample of that lineage graph. It's including file vertices that are colored by colored in red. This is why you see the sea of red, because one of the structural properties in that graph is that there were a lot more files than jobs. So that query, if instead we run it on a smaller graph view that preserves these job dependencies, but does away with all the files as well as their edges after preserving the job dependencies, then this query runs over a significantly smaller data set and can be answered much faster. So how do we do that? Well, again, we told you that the key contribution of our work is that we can leverage these structural properties of graphs for query optimization. Specifically, we introduce types of graph views that are necessarily sparser than the original graph, or that we can tell when they are sparser than the original graph. We call these connectors and summarizers. Connectors are obtained by a sequence of path contraction operations, and summarizers are akin to filters and aggregates in the relational setting. Constraint-based view enumeration is a notion we introduced, and it refers to this process of mining constraints from the graph schema as well as the data structural properties. and rewriting these queries in terms of beneficial views. And what I mean by beneficial, it's related to the cost model for these graph views. But unfortunately, we won't cover this at all. You can see the paper for a lot more additional details. Now, the graph view example that we hinted at earlier is what we call a two-hop connector. It's a special case of a connector. And here we show how to obtain one of those for a data lineage graph that follows the same schema as the one at Microsoft, or the example we've been using so far. So you have jobs in blue, files in red, and again, the same types of edges we talked about earlier. This is the original graph. Now in the next step, you augment this graph with two hop connector edges of different schemas here. In this case, these are same vertex type two hop connectors. And then what you get in the end is these two views, one for jobs only and one for files only. And notice, by the way, how some of the graph views, their structural properties may differ from the original graph. For example, the two-hop file connector is disconnected, whereas the original graph was connected. Anyway, so taking the magnitude of sizes for the machine-generated graph at the Microsoft cluster. So we had the original input raw graph with jobs, files, tasks, and machines, and that was in the order of billions and terabytes. Then once we built a graph view, a filter graph view on it that preserves only the job file relationships, then that reduces it to order of millions. And then when we go further, specifically for the job-less radius query, where it's possible to answer from a job-to-job lineage dependency graph, then you're talking about hundreds of thousands of nodes and a significantly smaller footprint on disk. Now, this is the architecture for Kaskade, which is a system we implemented as a proof of concept for these techniques. And it supports two main view-based operations. The first one is view selection. This is given a set of queries, identify the most useful views to materialize. And the second operation that it supports is view-based query rewriting. And this is determining how to rewrite an input query given a set of materialized views. And then one of the key contributions here is that we encode these constraint mining and view enumeration programs as first-order predicate logic rules. This turns out to be fairly powerful and surprisingly elegant, if you will. And we call this constraint-based view enumeration. Now, this is a workflow for a high-level workflow of constraint-based view enumeration. There are essentially two steps: query and schema, fact extraction, inference-based view enumeration. I'll give you examples of both of these, as well as examples of view candidates that this process infers. So taking as input the schema for a data lineage graph, the job file data lineage graph, its schema graph has two types of vertices and two types of edges. And the input query is the same one we looked at before. Now, these are explicit facts extracted from graph schema. The syntax here for the knowledge base for these facts is prolog, or it doesn't matter. You can think of this as data log as if it makes it easier for you. But the inference engine we use is SWI prolog, and this is written in prolog. So explicit facts extracted from queries graph pattern. Well, we'll go over into more details here. So the first one was a query vertex, right? And you extract the fact that it's of a certain type. You do the same for all the other vertices. Then for the edges, same thing. And then the trickier one is this special edge that the Cypher graph pattern syntax supports. And we have a specific predicate to encode that. So we call it query variable length path. It's kind of important because you can enumerate multiple paths from there. But anyway, the next step is constraint mining as inference rules. This is an example of a rule, or you can think of this as a program written in Prolog. And what it's doing here, it's mining implicit constraints using the inference rules over the explicit facts we extract, right? So an example rule here that's used as a building block for view templates is answering whether k-hop paths are possible between two vertices of specific type. And you don't have to pay too much attention to the actual syntax. If you don't, if you're not comfortable with Prolog, but essentially what I'm highlighting here is the fact that schema edge is a rule that binds with the explicit schema facts we extracted in the previous slide. Similarly, you have view templates using these constraint mining rules as building blocks. And the view templates themselves are also written as inference rules. So the example 2-hop connector view that we built from the job file data lineage graph is actually a specialization of a base template. And again, this is actually, is just a set of rules that need to be evaluated, right? And here's an example of query constraints that need to be satisfied for this K-hop connector view template to generate feasible view candidates. Here's the final step. So you infer view candidates given all the facts you gotten from the graph schema as well as the query graph pattern. And when you evaluate a specific view template here, in this case, K-hop connector same vertex type, you get a set of feasible view candidates. Now, not all view templates will produce feasible view candidates, and that's where the power of this approach lies as well. It constrains the search space for valid views that it can enumerate. So finally, the experimental results. This is a subset of the results we have in the paper. You can read the paper for more details. Suffice to say that we had essentially 2 classes of real-world graphs. The Prov one is the Microsoft provenance or data lineage graph. And the 2 at the top are highly structured graphs. So they have fixed schemas and they have structural properties that we can leverage for query optimization. And visually, every query benefits from being rewritten in terms of this summarizer and a 2-hop connector view. In the less structured graph, so these are homogeneous networks. If you're not familiar with the term, this essentially means that these networks or graphs, they only have one type of vertex and one type of edge, and these edges can connect any vertices in the graph. So we expected the views to be, the queries to be slower when answering in terms of those views, because the views of vertex-to-vertex connectors necessarily larger than the original graph in that case. However, we had a non-intuitive result that path queries on these still, at least for the road network, were still benefiting from being run over a 2-hop connector view. And one of the reasons for that is because it had a much larger fraction of long paths than the social network in comparison there. So in summary, the system that we designed and built performs automatic selection of sparser graph views using a number of different views that are, for example, K-hop variations or filters and aggregates. The view selection as well as enumeration and query writing are guided by this process that we call constraint-based view enumeration. We get significant performance gains, as I mentioned before, 50x faster response times, as well as significant reduction in size. So that's it. That's the summary, and here's my contact info. And thank you so much. Now I'd love to hear some questions.
Hey, I think you're muted.
Thank you. Thank you for reminding. I was telling you to unmute yourself. Thanks, please unmute. So I will go over the list of the questions typed, and you can check while I'm reading for the recording purposes. Zhou Wang asked, are there any differences between your work and the subgraph matching?
Yes, I mean, subgraph matching, the original problem talks about taking arbitrary graphs and trying to match one instance against another, right? But like, what makes that problem more challenging than what we're doing here is that you have essentially no information on the vertices, right? You don't match a specific ID to another ID. You can rotate the graph in multiple ways, right? So it's not an NP-hard problem, according to some recent results, but it's still a lot more challenging than what we're doing here in terms of at least complexity, right?
So, just to clarify, in your case, you you choose some patterns based on some mining and pre-compute those patterns for efficient query processing.
You can think of the pre-computing part as the materialization of graph views, right? But we don't pre-compute the patterns. We analyze the workload, we extract those constraints from the queries as well as the schema, and then we say, okay, which graph views are possible to pre-compute in the first place? And out of those, we have a cost model to determine which ones are more beneficial to pre-compute.
Okay. Let me go to Professor Aref. I say professor because I took my database class with him. So he is asking, in your job file graph, don't you have another edge type from file to file?
No, in that case, no. That's a good question. In that case, no. We do have a file-to-file relationship every 2 hops away, right? That's the file-to-file 2-hop connector example graph view that I introduced there. But we did not have, because files are essentially passive agents in that lineage graph. They're either read by jobs or tasks, or they're written to, but they're not directly connected to each other. You can certainly build a graph view that connects files with that, the 2-hop dependency links, but no, yeah.
Right, but in your match query, you have one edge which is up to 8 hops from file to file in your match query. So doesn't that mean that there are actually edges from file to file?
Yes, but if you remember, the query is specifying that you want to return only the source and the sink vertices in that graph pattern, right? So the edge in the middle, that variable length path edge, is just a way to connect those 2 jobs, essentially. It's filtering for those relationships. It's not considering all the other relationships, such as tasks and machines. It's there, but it's not what your query is trying to return. Your query just returns pairs of jobs, right?
I'm moving to the next question.
Jan
Pei is asking, very nice ideas and illustrated talk. In your constraint mining problem, would it find many constraints on a large graph? Do you need to prune some trivial constraints?
That's a pretty good question. It depends on the types of structural properties that you're trying to express in that language. I've only given you examples of connection properties there, but if you can think of things like, I don't know, I want to specify that paths in this graph view I'm building necessarily are time respecting, that the timestamps, if there are any, are monotonically increasing the same path, then obviously you can try and write more types of constraints there. But rather the constraints, at least the queries and schema ones, they're more of a function of the size of the queries as well as the size of the schemas, which are significantly smaller than the data graph, right?
There was a follow-up question. Jane, you can jump in if you want to unmute yourself and ask, but he is asking basically, will it be how many possible views in general to enumerate? Will it be a piece-based hard problem, or like?
Yeah, it is a function of the constraints you specify in your system, right? So the more constraints you add, the more you're limiting that search space, right? If you have no limits on this, then obviously the number of graph views is definitely piece-based hard.
So I think I'll stop the question session now. Please, again, we have a Slack after this, so you can continue the discussion and questions there. I encourage everyone to join the Slack after this. So let's go. Thanks, Joanna, for the answering questions.
Thank you.
Talk. So let's go to the next talk of this session, which will be paper 38. And we're okay. It will be given by Zhang. Again, I apologize for butchering names. The title of the paper is Efficient Top-K H-Structured Diversity Search. Zhang is currently a PhD candidate in Beijing Institute of Technology. Her current research interests include social network analysis and data-driven graph mining. Bo, please play the 38.
Hello, everyone. I'm Zhang from Beijing Institute of Technology. I'm going to talk about my paper entitled by Efficient Top-K Edge Structural Diversity Search. This is a joint work with Dr. Ronghua Li, Ms. Qi Xuanyang, Professor Guoren Wang, and Dr. Lu Qin. Now let's start. I will introduce my paper from 5 aspects: introduction, formulation, solution, experiments, and conclusion. In recent years, online social networks are becoming an important tool for human beings to interact with each other and spread information in the real life. A study reveals that the probability of social contagion relies mainly on the number of connected components in a user's neighborhood. Another research studies the structural diversity for a pair of vertices, which is measured by the number of connected components in their common neighborhood. Inspired by this work, we study the problem of finding the top K edges in a graph that have the highest structural diversities. The study can be useful for many applications. For example, in social networks, the edges with highest structural diversities may promote the information spread over different social circles. In scientific collaboration networks, the edges may improve collaboration over different communities. In natural language understanding, identify the edges is very useful for analyzing and understanding the meaning of the pair of the words in different semantic contexts. After the introduction, now let's come to the next part, formulation. First, we give the definition of edge-equal network. Consider the example graph. For the edge FG, its common neighbor is DEHI. So its edge-equal network is the subgraph induced by DEHI as shown in the shadowed area. Let's see the definition of edge structural diversity. Given a graph G and an integer tau, the edge structural diversity of UV in G is the number of connected components in UV's equal network with size no less than tau. Consider the example. When tau equals 2, due to the size of the two connected components DE and HI equals 2, so we have score FG equals 2. Well, tau equals 3, the score of FG equals 0 because there is no connected component whose size is bigger than 3. Based on the two definitions, we formulate our problem. Given a graph G and two integers K and tau, the top K edge structural diversity search problem is to identify the K edges in G with the highest structural diversities according to the component size threshold tau. Still consider the example graph. When tau equals 2 and K equals 3, the top K results are FG, HI, JK because their scores are equals to 2. Well, tau equals 5 and K equals 3. The top K results are UP, UQ, and PQ. They have one connected component with size equals 5. The challenges of our problem are as follows. How to efficiently prevent the edges that are definitely not contained in the top K results, and how to efficiently compute the structural diversities for all edges. After the problem formulation, it's time to introduce our solution. We first propose an online top K search framework. The general idea is that we first explore the edges in G with large upper bounds, because such edges may have a high chance of being the top K answers. We introduce two upper bounds of the edge structural diversity. One is mean degree upper bound. Here is the formulation. The other is common neighbor upper bound, and that's formulations. To further improve the efficiency, we propose a novel index-based solution. We first introduce the index structure. For each set of connected components appeared in all the edges ego networks, we create a sorted list by sorting the edges in a non-increasing order based on its score as the index structure. Consider the graph G. It's easy to derive that a set C is 1, 2, 4, 5. Therefore, we have 4 sorted lists, H1, H2, H4, and H5. Clearly, H1 contains all edges, because all edges ego networks have at least one connected component with sets no less than 1. The edges AB, AC, BC, BD, BE, CE, CG are not contained in H2, since the size of the maximum connected component in these edges ego networks is smaller than 2. Similarly, we can see that H4 contains 15 edges and H5 contains 3 edges. Based on the index structure, the query processing algorithm works as follows. For acquiring K-twa, the algorithm finds the sorted list HC, where C is the smallest integer in C, such that C no less than twa, and then reports the top K edges in HC. Reconsider the example graph. Suppose that twa equals 2 and K equals 3. The query processing algorithm first finds the index structure H2 because 2 is the smallest integer that is no less than twa. In H2, FG, HI, and JK have the highest structural diversities, so they are the answers. To construct the index structure, we propose 3 algorithms. The first one is ESD Index, which employs BFS to compute the connected components in edge ego network for each edge. The second one is ESD Index Plus. We give an observation as follows. Given an edge UV and its ego network, the 4 vertices UV, W1, W2 form a 4-click in G if and only if W1, W2 in its edge ego network. Let's see the example. For the edge FG, FG, DE form a 4-click in G and DE in its edge ego network. So we establish an interesting connection between our problem and the 4-click enumeration problem. So we present an efficient index constructor algorithm. The method is as follows. For each edge, we create a uniform set, and when finding a 4-click for each edge in this click, we merge the sets of the other 2 vertices in the uniform set. So when we search all 4 clicks in G, for each edge, all the connected components in its edge ego network are maintained in the uniform set. To list all 4 clicks, we propose PESD Index Plus to enumerate 4 clicks for each directed edge in parallel. In addition, we also devise efficient index maintenance techniques to handle dynamic graph. Based on 2 observations, the index can be maintained by local update methods. Here, we discuss the edge insertion. Below, we introduce an observation. After inserting an edge UV into G, the structural diversities of the edges in G hat need to be updated, and the structural diversities of the edges that are not in G hat remain unchanged. reconsider the example graph. Suppose that we insert an edge CD into G. G hat is shown in the left. By observation 2, the ego networks of our edges in G hat need to be updated. Take an edge DE as an example. The ego network of DE before inserting CD is shown in middle, where the vertices F and G form a connected component and the isolated vertex B forms another component. After inserting CD, we can see that the vertices B, C, D, E in G is a four-click. Thus, both B and C must be merged into the same component of DE's ego network. Similarly, C and G are also in the same component. Therefore, the ego network of DE contains only one connected component after inserting CD as shown in the right. For the case of edge deletion, it's similar to the insertion case, so we don't discuss here. Now we show our experiments. Here are the datasets. First, we compare the running time of OnlineBFS and OnlineBFS Plus. We can see that OnlineBFS Plus is faster than OnlineBFS due to the tighter upper bounds. We also compare the running time of OnlineBFS Plus and IndexSearch. Generally, on our datasets, IndexSearch is at least 4 orders of magnitude faster than OnlineBFS Plus. We compute the size of index and graph and evaluate the scalability of OnlineBFS Plus and IndexSearch. Then we evaluate the PESD Index Plus algorithms, and the results show great scalability and speed up ratio. We also calculate the running time of our index maintenance algorithms, and the results indicate that the algorithms are very efficient on real-life graph. We finally performed 2 case studies. The first one is on DBLP. We can see that our algorithm could be used to find the edges that maintain the connection with diverse structural contexts. Such edges may play important roles to promote the interactions between different communities in a network. The other one is on a word association network. The results indicate that our top K edge structural diversity search can be applied to find different meanings for a pair of words, which is a fundamental issue in natural language understanding. Finally, we conclude our paper. First, we propose a dequeue-twice online search algorithm with 2 upbounding rules. Second, we develop a new index structure to efficiently support the top K edge structural diversity search. Additionally, we also develop efficient index maintenance techniques to handle dynamic graphs. Finally, we conduct extensive experiments using 5 large real-life networks, and the results demonstrate the efficiency, scalability, and effectiveness of the proposed solutions. That's all my presentation. Thank you.
Thanks, Chi. So there are a couple of questions. I'll read the questions, and then please unmute yourself. I think you were here, Chi, right? I saw you earlier. I'm not so sure now whether she's here.
Hello.
Hi, okay. Good evening. So there were a couple of questions. Let me read them to you and please answer. Except for the definition, what is the difference of the edge structure diversity from vertex structure diversity in an application?
Okay.
So the difference between edge structure diversity and the vertex structure diversity.
The top K edges with highest structural diversity, the application has follows. First, in social networks, it can promote the information spread over different social circles, and in scientific collaboration networks, it can improve collaborations over different communities. And in natural language understanding, it can analyze and understanding the meanings of the pair of the words in different semantic contexts. So we do an experiment in DBLP and compared with the betweenness and common neighbors. The results show that the
Okay. Continue. We can continue discussion on Slack. Let me ask the next question. Hui Luo asks, how do you define the diversity, or are there any metrics for diversity in the problem definition?
The definition of edge structural diversity is defined by the common neighbors of the edges UV's common neighbors.
I see. So there is a definition. I think more details are in the paper of how it's defined, I guess, right? Okay. I don't see any other questions, and I don't have any other questions. So let's thank you again, G, for the presentation. So I virtually applaud everybody, unfortunately, lack of the things. So thanks. We'll go to the next talk now, which will be paper 79 by Zuo Wang. The title of the paper is Adaptive Relation Discovery from Focusing Seeds on Large Networks. Zuo Wang received PhD in computer science. Sorry, I cannot. From Harbin Institute of Technology in Darren. What is, sorry. I'm sorry. I cannot see the exact thing on my screen. Okay. So anyway, I have a technical issue with intention. So without further ado, let's present paper 79. Bo, please play the 79.
Dear authors, I am Wang Zhe, a student from the Chinese Academy of Sciences. Today, I'll introduce our paper, Relation Discovery from Focusing Seeds on Large Networks. Given a graph and a set of seeds related to each other, the relation discovery from focusing seeds finds additional vertices related to the given seeds. Such a problem is helpful for criminal group discovery on social networks. Here shows an example. In a social network, two users are adjacent if they are friends. Then, in a criminal case, the police find 3 suspects. Using RDFS methods, the police will find more people for inquiry with the known suspects and the social networks. The RDFS problem also has great potential value in other applications, such as product recommendation, semantic expansion, and protein prediction. However, not all the real-world applications ensure that all the given seeds are related to each other. For example, assume Tom is a fresh PhD student who is interested in data management. Then with the DBLP Cursor network and several research PC chairs of ICD 2020, Tom may want to discover popular topics in this area and influential scholars related to these topics. Ideally, 2 academic groups can be found. Tom can learn that social network and data security are 2 popular topics in DB area. Clearly, the presented example cannot guarantee seeds are related to each other. However, existing RDFS methods assume seeds are related to each other, which is not suitable for the presented occasion. Therefore, to support the application illustrated above, this paper proposes the adaptive relation discovery from focusing seeds. Given a network graph and set of seeds that may not relate to each other, recognize which seeds are related to each other. At the same time, discover vertices related to such seeds. Notably, the A-RDFS problem also supports the application of the general RDFS problem. To formalize the problem, we define the concepts of relation strings and alpha relation core to find vertices related to a subset of seeds which are related to each other. Thereafter, we design the relation quality to find a set of alpha relation cores containing all the given seeds, which shows the relations among all the seeds. Thereafter, several methods are developed to solve the A-RDFS problem. Here shows the first definition, the attraction. Given the graph and the set of seeds in the subgraph G', the attraction of a vertex V is defined as the following equation 1. In equation 1, heat Vt is the heat kernel diffusion, which measures a material V obtains from the start seed S. It is computed as equation 2. In equation 2, the vector H stores the heat values after heat kernel diffusion. Then let's go back to the equation 1. In the definition of attraction, the first term, the intersection of Is and Vg' makes the vertex V only sensitive to a subset of seeds. Thereafter, the attraction is determined by the minimum heat value, which requires a vertex with a large attraction value is related to each seed in the intersection of Is and G'. In the bottom left figure, the minimum heat value of V1 is 2.03. Hence, V1 is both related to S1 and S2. On contrary, in the bottom right figure, the minimum heat value of V1 is 0.04, which indicates that V1 is not related to at least one seed in the subgraph. Then the relation strength of a vertex V in the subgraph G' is defined as the following equation. In this equation, the filter function filters the vertices far from each seed. Then these neighbors are utilized to obtain a dense subgraph. Then an alpha relation core is a connected subgraph G' such that for each vertex in G', its relation strength value is no less than alpha. By maximizing the alpha value of an alpha relation core, we can obtain a dense subgraph where the vertices are related to a subset of seeds. The bottom shows an example. By maximizing the alpha value, we could get the subgraph in the bottom right figure. Then we define the relation quality. It is defined as the following equation. The first term, the intersection of Vg' and S, makes each discovered subgraph contain more seeds. Then the second term, the minimum of the relation strength, corresponds to the alpha value of each alpha relation core. Then to maximize the relation quality, we could achieve the following two things. First, alpha relation cores with large alpha values can be obtained, which discovers the vertices related to a subset of seeds. Then, in the alpha relation core with a large alpha value, seeds are related to each other. Both of the two advantages help to solve the A-RDFS problem. Then, the A-RDFS problem is formalized to maximize the relation quality. In the formalized problem, condition 1 is used to separate the seeds which are not related to each other, and condition 2 is just to maximize the relation quality. To solve the ARDFS problem, we propose three methods. They are opt-alpha, opt-split, and opt-A-RDFS. The opt-alpha algorithm maximizes the alpha value of an alpha relation call, which greatly removes a vertex with small relation strength values. Here shows an example. By iteratively remove those vertices with small relation strength values during the procedure, the subgraph with the maximum alpha value is returned as a subgraph. In this example, the subgraph in B is returned as a result. It has a relation quality which is equal to 17.08, which is much larger than the relation quality of G1. Thereafter, we propose the opt-split method. It separates an alpha relation call with a small alpha value into several alpha relation calls with large alpha values. Given a graph in A with the seeds S1 to S4, its relation quality is 0.12. Then in step B, the seeds are partitioned. Each seed is joined in the seeds where it achieves the largest attraction. Then in step C, similarly, each vertex is put with the seeds where it has the largest attraction. Then, by applying opt-alpha on each subgraph in figure C, we could get the subgraphs in figure D. They are the resulted subgraph. Their relation quality is 13.06, which is much larger than the relation quality of the subgraph in A. Then we propose the opt-A-RDFS on large networks. In the first step, the HK-relax method is utilized to approximate the vertices with positive heat values, which prunes a large amount of vertices on large networks. Then, by iteratively increasing the relation quality utilizing opt-alpha and opt-split, we could get a set of alpha relation calls with large relation quality. Here is an experiment. In our experiment, the networks evaluated are shown in the figure, shown in the table. They are available from website, and for each network, they provide 5,000 high-quality ground truth communities. The baselines used in our paper are shown in the bottom left part. They are existing RDFS methods. The first 5 methods are community search, and the last 3 methods are local computation methods. Then we generate our queries as shown in the upright part. Firstly, given the network, we randomly fetch 5 communities CT from the ground truth communities. Then from CT, we randomly select 15 vertices as the focusing seeds. Thereafter, from the network, we fetch 5 extra vertices. Then the query consists of the selected 20 vertices. Totally, for each network, we generate 1,000 queries for evaluation. The metrics are shown in the bottom right part. F1 is used to measure the accuracy of the comparing methods. Conductance and density are used to measure the quality of the resulting subgraphs. Furthermore, we also test the average running time of each comparing method. This slide shows the accuracy of the comparing methods. Among the methods, A to H represents the baselines and I is our method, opt-A-RDFS. According to the data, our method achieves the best performance. This is because our method can automatically recognize which seeds are related to each other. Besides, our method finds the vertices which are close and densely connected to the given seeds, which ensures the structure quality of the resulted subgraphs. Both of the 2 reasons account for the accuracy of our method. This shows the efficiency evaluation. Among them, I is our method. We can see that our method is efficient on most networks compared to the community search methods. Our method needn't guarantee the connectivity of all the given seeds. As a result, our method is competitive with the local commutation methods such as HK. However, our method needs more time to deal with output. This is because on output, the average size of ground truth communities is large. For accuracy, our method had to use a small error tolerance to approximate the heat values, which requires more time on output. This slide shows the parameter evaluation. Our method has 3 parameters. T and epsilon are used to compute the heat values, and the last beta is a weighting factor in relation quality. The first 4 figures show that when T is small, our method is efficient, and the resulting subgraphs have good structure qualities. Figure E to H shows the performance varying with epsilon. When epsilon becomes larger, our method is faster. However, this means the found vertices tend to be fewer, which results in lower quality and accuracy. The last 4 figure shows when beta is large, more relations among focusing seeds can be found easier. Here, finally, we show a case study. The focusing seeds are the scholars who are active in the Journal of Expert System Applications. The middle figure shows a subgraph found by an existing RDFS method. In such a subgraph, many scholars do not have the same background with the selected scholars. On contrary, the right figure shows the subgraphs found by our method. The figure A shows a subgraph about geographical information processing, and the subgraph in B shows the fuzzy control group. Both of the 2 subgraphs demonstrate the performance of our method. In conclusion, this paper studies the A-RDFS problem. Existing RDFS methods assume the given seeds are related to each other. However, in many real applications, such assumption is not guaranteed. So we study the adaptive relation discovery from focusing seeds to support such applications. Then we propose and formalize the problem and propose 3 effective methods: opt-alpha, opt-split, and opt-A-RDFS. Extensive experimental results demonstrate the performance of the proposed method. In future works, we will extend the A-RDFS method on other kinds of such graphs, such as attributed graphs and evolving graphs. That's all. Thank you.
Okay, thank you so much for the presentation. I don't see anyone typing a question, but I have a clarification question though. By the way, sorry for not properly reading it. So Zhou Wang received the BS degree in computer engineering from Harbin Institute of Technology in 2014. He's currently pursuing the PhD degree in Institute of Information Engineering, Chinese Academy of Sciences, and his main interest includes social networks and graph algorithms. So I had an issue with the online Google Doc, so couldn't read it correctly. So my question is that how important are the seeds that you select to start this process? Do they have to have special properties? Is it sensitive to the starting seeds, or how sensitive? Have you done some sensitivity analysis?
Yes, thanks for your question. We study the problem on simple graphs, which means they don't have attributes. They just the vertices. It's just the topology graph. We just study our problem on topology graphs. In our experiment, the seeds are selected from different ground truth communities, and this is what we want to study our problem. So we select the seeds from many different ground truth communities and try to use our method to recover these ground truth communities. So this is the key distinction between our method and the existing methods. Maybe.
Yeah, I got it. Thank you. Thanks for clarification. Are there any other questions people have? I don't see anything on the chat window. Going once, twice, third. I think, thank you so much for the presentation. And again, I encourage everybody to follow up the discussion on Slack. It's harder to do both I know during the session, but after the session, please do ask and interact via Slack. Thank you.
Thank you.
So let's go for the last talk of this session, which is paper 379. It's going to be presented by Peng Lin, repairing entities using star constraints in multi-relational graphs. Peng Lin is the fifth-year PhD student from Washington State University. His PhD advisor is Dr. Yinghui Wu from Case Western Reserve University. So, Bo, please play 379.
Hi, this is Peng Lin from Washington State University. I'm gonna present our paper repairing entities using star constraints in multi-relational graphs. We start with a knowledge graph about football players, clubs, stadiums, and for each node, there are a couple of attributes such as name, owner, and the city. However, this graph has two incorrect attributes. The city of V2, which is Leeds, but it should be Manchester as the city of V1. As there is no direct edges between V1 and V2, how can we identify these errors? One way to identify these errors is some semantic association in the neighborhood. Constraint states that for stadium and facility relevant to player from Premier League, if they have the same owner, then they should locate at the same city. But as the graph is very heterogeneous and there are many different types of edges, how can we encode such constraints? We observe it can be encoded as regular expressions, which can be a single edge label or edge labels repeated up to k times, or the combinations of sub-expressions by disjunction or concatenations. For example, to find the path from the player to stadium, regular expression R1 can be placed for, operates, or coached by, works at. So similarly, finding the relevant path from player to facility, the R2 can be placed for, operates, teammate less than 1 times, and trains at. So based on these observations, this paper studies the central problem of error detection and repair for the graph data using constraints. And the input is a graph does not satisfy constraints, and the output graph G prime satisfies the constraints. We propose a new constraint for graphs, namely star functional dependencies or simply star FDs. We formalize the entity repair problem following the minimum editing cost principle, and we found that problem is NP hard and hard to approximate. Despite the hardness, we propose a feasible framework with probable guarantees whenever possible. In the repair workflow, we partition the inconsistencies as optimal, approximable, and heuristic cases. And then for each of them, we have some performance guarantee. So we start with the formal definitions of star constraints. It has some star pattern PU0, which is a two-level tree with the center node U0. And each branch of the pattern is a regular expression, as we introduced before. And for the value constraints x, y, it means if x holds, then y should be hold. X and y are two sets of literals, and each literal is either in the form of u dot a equals to a constant value c, or equivalence of two node attributes. So in the previous constraint, it can be encoded as u0 dot league equals to Premier League, and u1 the owner equals to u2 the owner, and the literal can be encoded as u1 the city equals to u2 the city. To identify the errors, we need to locate the fraction of graph data matched by the star pattern, and we adopt the maximally site match. So in this example, the center node U0 matches V0, and from V0, we search the neighborhood of the data guided by the regular queries, and we can find that the maximal set of nodes can be matched by U1 and U2 respectively. So for example, U1 matches the stadium V1 and V4, and the facility U2 matches the facility V2 and V3. And to capture the inconsistencies, we define them as matches that X holds but Y does not hold. In this example, let's say the city of V2, for every stadium that has the same owner as V2, they have different values of city. Then the whole match set is an inconsistency in our definition. Now we have our pattern as star FDs. We summarize the major results of this paper. We studied some fundamental problems such as satisfiability and implication. The satisfiability problem input is a constraint sigma. It is to decide whether there exists a graph G that satisfies sigma. If not, there is no way to repair the graph. And this problem is NP complete by showing a reduction from the conditional functional dependency satisfiability problem in relational tables, which is an NP hard problem. And for the implication problem, given input sigma and a single constraint phi, decide whether for all graphs satisfy sigma, do they also satisfy phi? So this problem can help detect and remove redundancy of constraints in a set of constraints sigma. And this problem is co-NP hard by showing a reduction from non-equivalent problem of regular expressions without clean stars. And that problem is a NP hard problem, which can be reduced to the complement problem of implication. And we also are interested in the practical problems such as error detection and repair. The error detection input is graph G and constraint sigma, and output is all inconsistencies I. And luckily, this problem has a p-time algorithm by first evaluating regular path queries and then validate value constraints. And for the repair problem, given the sigma and the graph G that does not satisfy sigma, and output a graph G prime that satisfies sigma with the least repair cost. Unfortunately, this problem is NP hard and hard to approximate. So despite the hardness, we adopt a dichotomous approach that partitions inconsistencies into optimal cases, approximable cases, and heuristic cases whenever possible. And each of them has some performance guarantee. Now let's study how to repair the graph. We begin with the concept of updates and repairs. Updates O means a set of operators with editing cost. Each operator is to change the node attribute v.a from its original value small a to the new value small c. And the total cost of updates is sum of cost over each operator. And we say updates O is a repair if applying the operators O to the graph G such that obtain G prime that satisfies sigma. In our example, we may have two repairs. One is to change the cities of V2 and V4 to the cities of V1 and V3 respectively. Another one is to change the owner of V2 and V4 such that violate literal conditions in the X literals. So now we have the formal definition of entity repair problem. So given sigma and the graph G does not satisfy sigma, output a repair O or equivalent a graph G prime that satisfies sigma, and the cost of O is minimized. This problem is hard, as we mentioned, and we have some observation that for some cases, there are approximable cases. We see some inconsistencies are connected at the shared node attributes. In this example, we have three inconsistencies in color paths. And for example, V1.A1 is a node attribute that can affect conditions of literals in both of inconsistency I1 and I2. So we say I1 and I2 are connected. The three inconsistencies form a whole connected components, or simply CCs. And we define isolated CCs as no new inconsistency is introduced when this CC is repaired. And isolated CC has approximate solutions. That's inspire our dichotomous framework of repair. So if it's approximable, we further ask whether it's optimal repairable. If the isolated CC form a hyperstar structure like this figure, then we call it is optimal cases, because it has a solution like this. We can either select the updates with the least cost inside each of the petals of the hyperstar, or we can select the one updates all with the least cost in the center, and then we read the one with less cost. So for example, in the center, OL1 has a less cost. And in each petal, we select OL3, OL5, and OL6, and we induce output big O. And we found the big O has a higher cost, then we return the O star. For the approximable cases, it doesn't have the hyperstar structures, and we observe it can be solved by a minimum hypergraph vertex cover without forbidden pairs. Intuitively, if every inconsistency is covered by some updates, by flipping the condition of literal in X or Y, then that inconsistency is repaired. However, some updates OL may conflict each other. For this example, OL5 and OL6 change the same node attributes to different values. Then they may not coexist. And in that case, if we select OL5 and OL6 is pruned, and then we return OL5 and OL2 in this cover. For the heuristic case, note that now the CC is non-isolated, and repairing this area may introduce new inconsistencies. And we select CC introducing fewest inconsistencies. And in this example, it's CC1. And after we repair it, we introduce the new two inconsistencies, I4 and I5. And each of them has their own CC. And after we detect this inconsistency, we repeat the selection of a next CC with the least new inconsistencies until incur a cost bound. And we show this solution has a bounded repair cost. Okay, so we experimentally verify our solutions and on the 4 real-world dataset, including knowledge graphs, business reviews, and movie network. And to generate errors, we adopt a silver standard and error generation benchmark, because the real ground truth is hard to obtain. And the silver standard believed the dataset has the ground truth. And for the star FD generation, we built an algorithm discovering the top frequent star patterns and value constraints with high support and constraint. Also, they are discovered from silver standard. And we built 3 algorithms. The first one, star repair. It uses bidirectional search for regular path queries and uses incremental error detection in the heuristic repair. And for BFS repair, it doesn't use incremental error detection. And for sub-ISO repair, it uses subgraph isomorphism as matching semantics instead of regular path queries. For the efficiency, star repair outperforms BFS repair by 3.4 times due to the incremental error detection. And it outperforms the sub-ISO repair by 7.5 times due to it uses regular path queries instead of sub-isomorphism. And for effectiveness, star repair outperforms the sub-ISO repair by 10% in F-score on average, and 9% in precipitation, and 14% in recall on average. This is because regular path queries can summarize the diversified paths well in the heterogeneous graphs, whereas the subgraph isomorphism will enumerate every subgraph in neighborhood and have a lot of overlapped graph patterns and matches, which lower the accuracy of approximable case. We don't compare it with BFS repair since they have the same matches, and the accuracy is the same as star repair. We have real-world case studies. In this example, President Bush, a child, is labeled as President Obama, which is wrong. This is a real example in Yago, and we found a star FD states that if a person who is a politician or president of United States and is married to another person, then they should have the same child. As Bush is president of the United States and is married to Laura, who has a child, Barbara, then this inconsistency is captured successfully by our star FD. Okay, we realize another graph constraints, namely graph functional dependencies. And we have a quick compare here. GFDs adopt subgraph isomorphism as a matching semantics, whereas StarFDs uses star patterns with regular expression queries. They also have different complexity and hardness in satisfiability, implication, and error detection problems. And in the error detection part, StarFDs can detect the errors in polynomial time. Okay, this is our paper. We propose a new star constraint with regular path queries, and we start the satisfiability problem, implication problem, error detection, and the repair problems. And for the repair problems, we adopt the dichotomous strategy to partition inconsistencies with optimal cases, approximable cases, heuristic cases with a performance guarantee. Okay, and that's it. Thanks you for watching. And by the way, our research group is exploring domain-specific applications of knowledge graph quality. And we have a paper in demo session, and welcome to check out. Thanks.
Thank you all. I wonder whether there's any questions to Peng. Peng is sharing his video and questions. Are there any questions? So looks like we don't have any questions. Peng, you at the end you had this comparison about computational costs and so on. So what's the largest network you have tried this technique?
Excuse me, would you say it again?
Yeah, sure. So it looks like the technique that you are doing is kind of expensive. So what's the largest graph that you applied this?
Oh, the largest graph. We have applied it to the 4 real-world graphs like Yago and the DBP there. And the largest graphs we have applied, I believe, it's millions of edges and up to 10 millions of nodes and up to 10 millions of edges.
How long does it take?
Runtime. I think if we applied about 100 StarFDs constraints, it's about a few seconds up to a few minutes.
Okay, that's good. Thank you. Any other questions? Thanks, Peng. So as I mentioned, there's a Slack channel. Please, if you have any further questions, join the channel. It's on the program page. So I will, if there are no questions, I will close the session. Please note that in 23 minutes, we will have the second keynote of the day coming up. Again, the Zoom link is available via the program page that you all received. Thank you all for attending, and thank you all for the speakers to join for answering questions and preparing the videos. Hope to see you in 23 minutes in the session. Bob, please stop recording, I guess, and we can leave the meeting. We will reopen it after the keynote.